Okay, I think we can start. Let me share my screen. Here, can you let other people in? In the chat, can you see my red mouse moving? Just say yes, anybody. Okay, awesome. Okay, I think we can start. If you have any questions, feel free to text to the chat. I will see that. And when I make a pause, I will answer it. So today we are going to cover two topics. First of them is splay tree and then Lincoln tree. So splay tree. Splay tree is a little bit similar to the trip. The same as trip. Let me move it. How can I move it? Okay, whatever. The same as the trip, it's a binary search tree, so that we have some tree. Each vertex has at most two sons, two children, left one and right one. And some of them can have only one, like 10 here, and some of them can have none, like one here. But the difference is that in splay tree, when we are trying to find some vertex, and after we find it, for example, 6, after we find it, we will try to push it to the root. So when we have a query to find vertex 6, we will move here and then push it to the root. However, we cannot just swap the values 8 to 6 and 6 to 8, because if we do it, our binary search tree will be broken, because so 6 will be here, and if we want to find 8, we will need to move to the right, because it's binary search tree. However, our 8 will be located here in the left part. So we should be able to push it in some different way. Okay, let's talk about explicit splay tree right now. Explicit means that for each vertex, we have some value. So like 6, 3, 8, and this value is given. So for example, in input data, it says that we have a vertex that has some key. So it's called explicit. And also there are implicit. It means that they have just some values and the keys depend on the location. So like this is number 1, number 2, number 3, number 4, number 5, 6, 7, 8, and 10. Now we are going to talk only about explicit as splay tree. So it's the structure of some vertex in splay tree is very similar to trip. So we have some key that is given to us. We have links to the left and right sons, but we also have one more link. It's linked to the parent, P. And we have, and let T node be just a link to a node. So first we should learn a few more functions. So set parent, obviously it means that for some node child, we say that parent is its parent. So we should be sure that child is not null. And if it is not null, we're just setting its parent to P. And we have one more function, keep parent. It updates the parents for its children. So we are going to look at our children and update their parents. So any questions about that? Okay, I don't see any. Okay, so then if we want to push some vertex to the root, we should be able to rotate them. So if we have vertex x that we want to push, and it has some vertex y which is its parent, so we should change it to some we should change it in some such way. So if we have vertex x and vertex y, we also have three other subtrees. Subtree alpha, where all the values are smaller than x. Subtree b, where all the values are bigger than x but smaller than y. And subtree gamma, where all the values are bigger than y. So let's look at this example. If we have x here, then alpha should be still there. Like alpha should be smaller than x, and it's still there. And it works. The same for gamma. Gamma here was the right sum of y, and here is the right sum of y as well. However, the location of beta is changed. It was the right sum of x, and now it is the left sum of y. So let's make sure that it's located in right location. So here in the left example, we will access beta subtree only if, so here, if we want to get to b, some value should be smaller than y and bigger than x. So all the values in beta are bigger than x and smaller than y. And here, if we want to get to b, we should go to the right from x. So it should be bigger than x and smaller than y. So we have that all the properties of beta here is the same as beta here. So let's look how can we implement that. So we are going to have a function rotate. If y has a parent, let's call it grandparent, we should change the son of our grandparent. So we are doing this in this line. We want to find if y is left or right son of our grandparent, and then change it to child to x. And then we want to understand if x is left or right son of y. If it is left, so just do that I just explained to you. So you're saying that the left son of y will be beta, and the right son of x will be y. If x is as the right son of y, so just do the opposite comments. And after that, the parents, the children of our x and y will be changed. So we should keep everything updated. So we are calling keep parent for child and parent. And also the parent of x will be changed. It's not y anymore, but it's the grandparent. Okay, any questions? Okay, let's continue. So we may want to push not only in one level, but in two levels. So like if we have some vertex v that we want to rotate, and we have vertex p, which is its parent, and vertex g, which is its grandparent. So it's better to rotate them in such way. First, we rotate p and g, and we will get such tree. And then we rotate v and p, and we will get such tree. And it's called zig-zig because V for P is the same as P for G. So V is the left sign for P and P is the left sign for G. And we would also use zigzag technique when V is the right sign for P and P is the right sign for G. But we also can have the zigzag situation. It's when V for P is not the same as P for G. So one of them is the left sign and another one is right sign. So what we can do there? So we just rotate V and P and we will get such situation, and rotate V and G and we will get this. So let's see how can we implement that. So let's call this function display. This function will push our vertex to the root and return it. So if this vertex doesn't have any parent, it means that it's already root, and we just return it. If this vertex doesn't have a grandparent, we just rotate it with its parent and return it. Then we should be able to understand if it is zigzag or zigzag situation. So in order to understand that, we should look at this equation. So this equation will be true if our vertex V is the left son of parent, and this equation will be true if our parent is the left son of grandparent. So this total equation will be true only if these two equations are equal. So it means that it's either true and true or false and false. If they are different, we will do zigzag. If they are equal, we will do zigzag. If they are different, we are going to do zigzag. Yes, zigzag. So, and after we do that, we will splice it again until we find the root. Okay, any questions about that? Okay. Let's implement what is only when this is only when V is depth of 2. No, so we are going to do zigzag or zigzag always when it has at least depth 2. We are going just to rotate it in this way only if this vertex is next to the root. So if it is next to the root, it means that we cannot make either zigzag or zigzag because it requires at least 2 nodes, like at least this node and 2 more. But if it is next to the root, we have only 1, so we just should rotate it. But otherwise, we will do zigzag and zigzag. Okay, any other questions? Why cannot we use rotates for zigzag for solve zigzag? Rotates for zigzag. Okay, so you see that the order for zigzag and zigzag are different. So here in zigzag, we first rotate P and G. So not V. So that nodes that we need to push, we don't rotate firstly. Firstly, we rotate P and G, and only after that we rotate V and P. However, in zigzag, we just rotated V with P and then V with G. Why you can just rotate with parent instead of doing zigzag and zigzag? So the thing is that if we just rotate like one by one, like using function rotate, there can be trees, there can be a long tree. So the depth of some vertex can become very long, very depth. So, but if we use zigzag and zigzag, it will sort of stabilize the depth of the tree so that it will be around log n. Other zigzag? No, there are no. So there is either zigzag or zigzag, but not zigzag. Okay, so I think we can continue. Okay, probably yes. So we are going to learn a new function find, which will find vertex based on the key. So if our node is empty, we just return null. If we already find if this vertex has that key that we are looking for, we will just push this vertex and return it. And then we compare it. So, and then we should be able to understand if we want to go to the left or to the right. If our key in this vertex is bigger than what we are looking for, then obviously we should go to the left, and otherwise to the right. And please note that we have one more thing in the if statement. If am I leave? What happened? Can you say yes in the chat? Okay. I don't know what happened, but okay, let's continue. So what was I talking about? Okay, so if we have, if we don't, so we should also check that left sun exists, and only then, and only if it exists, we can go there. So why we should do that? It's because when we don't find a vertex, so let's say we have only elements 1 and 3, but we don't have 2, we should say that this vertex does not exist. However, if it does not exist, we will repeat all this way. Okay, let me come back to this example. Okay, so let's say we want to find, for example, 15. So we will start with 8, we will go there, we will go there, and then here we understand that 15 does not exist. So if our next query will be 15, we will go this path one more time. However, this is not what we want. So the logic of split tree is to answer very fast for the most common queries or most recent queries. So if we ask for 14, we will push it to the root. And for the next query, if we ask 14 one more time, we will get 14 in one operation. However, if we do 15, we will just move to 14 each time. And each time we will get that 15 does not exist. So if it is like 3 operations, it's not so bad. But if like it's, I don't know, like a lot of vertices, it will be bad because we are going to iterate over the same set of vertices each time. So this is not what we want. Even so, it means that even if we don't find a vertex, we will push the last vertex that we looked at. So in this example, if we want to find 15, we'll start with 8, continue to 10, continue to 14, and here we understand that 15 should be to the right, but there is nothing to the right. So we will push 14 to the root. And next time, when we want to find 15, we will start with the root 14, and then we will see that 15 does not exist. And what if request a random? So if it is random, then it's going to be around like log n in average. Let's play. Okay, so here, so we should check that left vertex exists, and the same here, that right vertex exists. If if none of these statements are true, then it means that we did not find that. We did not find that vertex, and we just need to push the last vertex that we looked at. So, and what that is what we are doing here. Split. So our split will split some splay tree into two parts. In the first one, the keys should be smaller than key, and in the second one, the keys should be greater or equal to key. So it's pretty similar to the trip split, but yeah, let's go over it very fast. So if T does not exist, then L and R are null. Otherwise, we are going to find this vertex key. So you remember that even if key does not exist, we will find some vertex which is close to key. So we are comparing it. So if key is smaller than, if our key in T is smaller than key, then it means that this vertex should be in the left part, and all the vertices in the right sum of T should be in the right part. So you remember that if T key is smaller than key, it means that key does not exist in this play tree. So so if it does not exist, we will find either left value of key. So it means we will find either the closest to the left or the closest to the right. So if this equation is true, it means that we found the closest to key to the left. So the biggest number that is smaller than key. So that is why we can be sure that all the vertices in TR will be greater or just greater than key. So we are just erasing it. We are saying that R is TR and LR is just T. Why we need find here? We don't have to use find here. So if you want, you can rewrite this function using like on your own without find function. But here I just use it for simplicity. So just to show that we can do that. If you want, you can rewrite it without find. So, and if this does not hold, if it is not true, then our vertex in T is a key or greater than our key. So if we find if key does exist in our tree, we will find it. And if this equation does not hold, then our value in T is greater than key. So, but in any case, this vertex should be in the right part, and all elements in the left sum should be in the left part. So we just do the opposite operations from this one. So any questions about the split? Okay, let's continue. So merge. So we are going to combine two split trees into one. So, but for that we should all the keys in the left one should be smaller than all the keys in the right one. So if we try to find in R any vertex with L key, we should get the very first element. That's because like all the keys in L should be smaller than R. So in any case, we should just go all the time to the left until we find the smallest element. So if we do find, it means that our root will be the smallest element, and we are going to have just non-elements in the left sun. All other elements of R will be in the right sun. So we are just saying that our left sun is L and just updating everything. Does it make sense? Do you have any questions? Okay, let's continue. And insert. We are going to insert some vertex with some key. So first we should, the same, it's pretty similar to the tip. We are going to split our tree into two parts, where in the first one, all the elements should be smaller than key, and in the right one, all the elements should be greater than key. So we are splitting it into L and R. Then we are creating another a new node with key, and we are just merging it. Merge L with V and merge the result with R. Any questions about that? Okay, so, and now let's talk about implicit splay tree. What is the average days depth of this tree around log n? Why? There is a long proof. I don't really want to go over this. If you want, I can send you the link to the proof, and you will be able to read that. Okay, let's continue. So in implicit splay tree, we are not going to have some, so we are not going to compare the keys. We are going to save, so for each vertex, we will be able to get its like location based on the number of vertices to the left. If we have queries like very small and very large key, then push it to the root will not make sense, does it? If we have queries like very small and very large key, then pushing to the root will make no sense. If we have queries like very small, query number one, find -1. Okay, so I didn't really get what you mean, but I think if we're going to have like very small and very large, then our splay tree will be like sort of divided into two parts. That part where all the elements are smaller, are like very small, and other elements where all of them are very big. So if we have, oh, okay, I think I got what you mean. So if we have some list of keys, and we are going to find like the smallest one and the biggest one. I think that's what you mean. So if we want to find the smallest one, we'll just push it to the root. And so the smallest element is the root right now. If we want to push the biggest one, we'll make the root of this. And this, the smallest, will be the left sun of that. Okay, not the left sun, but maybe the second sun of that. Like the smallest will be located in the depth 2 from the root. And next step, if you want to find the smallest one more time, you will go there using two operations. Because it's located like it's the new root is the grandparent of the smallest element. And after you push it one more time, the greatest element will be located like it will be the right side of the right side of the root. So if you have such type of queries like very small and very big, you will be able to find each of them like in 2 operations. Does it answer your question? Yes, exactly. Awesome. Okay, so let's talk about implicit split tree right now. So here we are going to, so if you know tree, it will be easier for you. We are going to have size. Size is the number of elements in that subtree, in the subtree where this vertex is located, so including this. So in M, we are going to store the minimum, and key is some, and key, so the minimum among keys in some subtree. So when we just create a new node based on the key, we are going to have only one element. Can be M, can be anything. So yeah, it can be anything. Minimum is just for example. It can be some, like we have, yeah, it can be some, it can be maximum, it can be XOR, and many other operations. So just, but for this example, we are thinking it's minimum. So we are saying that minimum, if we have only one element, we are saying that minimum is equal to this key. And yes, I think it's the only differences in the node. Okay, let's continue. So some extra functions. If we want to get the size, we just get in the size, but first we should check that v exists. If it does not exist, we just return null, return 0. The same with getMin. If v exists, we return minimum. If it does not exist, we return maximum. And update function. In update function, we also should be sure that v exists. And if it does exist, we are getting the sizes of other children and updating the size of this vertex. So this is this vertex 1 plus all the nodes in the left child and all the nodes in the right child. And exactly same logic behind minimum. We are getting finding minimum among this key and minimum among left and right children. Okay, any questions? Okay, let's continue. Split. So here we are going to split into 2 parts. So the key now is, so we are going to split into 2 parts. In the first one, we are going to have key elements. So if we have key equal to 5, it means that in the left part, we should have exactly 5 elements. So if t doesn't exist, we just return null. If key is 0, it means that we should have empty left part. So we're just saying that L is null and R is over T. And the same if key is the same. So if in the left, if key is equal to the size of T, it means that all the vertices in T should be in L and R should be empty. So we just saying that R is null and L is T. Otherwise, we want to find the vertex that will split T into 2 parts. The left one where all the elements are smaller than, so here in find, we want to find key plus first element. So we want to find the first element that will not be in our left node. So we are sure that this vertex does exist because if it did not exist, we would have true in this if statement. But since this equation does not hold, it means that we have at least, and based on these two equations, we have that in the left part, we are going to have at least one element, and in the right part, we also will have at least one element. So we are going to find the first element that does not exist. The first element that will not be in our left node. So we are finding that, and then when we find that, all our elements that will need to be in the L node will be just in TL. So we just erase TL from T and updating everything. Okay, any questions about that? Okay, let's continue. So merge is pretty similar. We are finding the first element in R, and just to be sure that to the left we don't have anything. Like to the left from R, we don't have anything. So if we are sure that that's true, we can just say that the left child of R is our L. So this is pretty similar to that merge that I showed you before. Okay, and get mean. So what if we want to find the minimum in some range? So I think it's like exactly the same code for the trip. We are just splitting our splay tree into 3 parts. The first one is so the second one is that splay tree that is located exactly between L and R. The first one is where all the elements are smaller than L, and the third one where all the elements are greater than R. So we are going to store this in T1, T2, and T3. So we are interested only in T2. So that is why we are going to find the minimum of that, then merge it and return ends. So, and what if we want to insert in some position some value? Then we need to split it into 2 parts. That in the T1 we are going to store all the nodes that will be to the left of both, and in T3 we're going to store all the nodes that will be to the right of both. So that is what we are doing here in split. Then in T2 we are going to have just this node, and after we create it, we will match T1 with T2 and then with T3. Okay, any questions about that? Because that's it for splay tree that I have for you. So let's ask all the questions we have about splay tree, and we will continue with the linker tree. Is it better to trip? It depends. So in some problems, we can have such situation when we ask our queries for some nodes more often than to the others. So for some vertices, we can like ask them like 1-2 times, and to other we can ask like 10, 100, or even more times. So in this case, when like our expected number of queries for each vertex is not the same, it's better to use splay tree, because in splay tree we are going to store the most recent nodes closer to the root. When in trip it's pretty random. Okay, any other questions? How do we build it? So we just like create, yes, adding one by one. So like using, I don't know, for example, add here, and yeah, that's it. But only one by one will be linear time. Yeah, so it's in total it's going to be n log n. Not really. It's not going. So, are you going to? Are you talking about implicit or explicit nodes? Explicit split tree. So right now we were talking about implicit. Someone has microphone on. Could you please? Oh, is it you? Yeah. If you have if you want to talk about to ask a question, yes, please do that. So, Ostap, do you still have like your question, or you already understand? I played with it. Okay. Okay. Any other questions about Splay 3? Okay, so I don't think so. So we are going to learn Linka 3. So it's I think the most similar data structure to Linka 3 is heavy light decomposition, but it's still a little bit different. And so in heavy light decomposition, in preprocessing, we find which edges will be heavy and light. And then after we build that, it's going to be static. We don't change it in the queries. But here in Litka 3, we are going to have heavy and light edges as well, but they will be dynamic. We will change them depending on our queries. So here in Linka 3, we are going to have some root, for example, this vertex, and we're going to have some heavy edges. So we have a few rules that from each vertex, we can have at most heavy edge that is going to the suns. So for this vertex, among these three edges, only one of them can be heavy. And for each vertex, we can have its parent edge to be heavy, and it doesn't count. So like for this vertex, this edge is light, and this vertex, this edge is heavy, but we still can have one heavy edge in the suns. So you see that in such example, we have a few paths. We have such path, we have such path, and we have such paths. And on each such path, we are going to have some data structure. For example, in heavy light decompositions, if I'm not mistaken, the most common data structure is segment tree. Here, segment tree doesn't work with us because the size of static tree is static. But other sizes of these paths can be changed. So we will use is the trip or splay tree. So how do we mark? Okay, as heavy. I will tell you right now. So by default, all of them will be light. And if we have some query, like in this problem, we can ask some questions like find the minimum weight between some vertex and the root, or find the and change the value of some vertex, for example, or change the value of some edge, and find the minimum between some vertex and the root. So if we have some query, for example, such vertex, we should make a path between this vertex and the root. However, between them we have a few light edges. If it was a heavy light decomposition, we would just find the answer on this prefix in segment 3, for example. Then check this, find some answer for the prefix here, and so on. Here we are going to use some similar idea, but we're going to change the tree depending on our queries. So, if we have such query, we will find the answer here. And then we want to make this edge heavy as well. However, in order to make it heavy, we should make this edge light. So in order to do that, we should break this path. So what we can do? So let's say it's splay tree. So in each path, we store a splay tree. So we should find this vertex, the vertex that means that is for this edge, and remove it. Split it into 3 parts. Sorry. The first one is everything this vertex and everything that is upper. The second one is just as this edge, and third one is this edge and everything to the lower. Each heavy path is splay tree. Yes, it is. Or it can be trip. For this example, we are saying that it's a splay tree. So after we separate it into 3 parts, we should not have a splay tree for this edge anymore. We are going to have this splay tree here. And this splay tree, we are going to combine with this edge and this splay tree. So after we make this iteration, we are going to have a path from here to here. But if we are located in this vertex, we have one more light edge here. So we should repeat everything that I just said. We should make this edge light and make this edge heavy. So we need to remove this from this splay tree and add this edge to here. So after that, we are going to have such path. Okay, any questions about the idea behind that? So we are not talking about implementation, how can we write it? So how do you have any questions about what we should do in theory? What is heavy edge? Heavy edge is edge that we like used. So like if we have some query, all the edges will be heavy between this vertex and the root, and they will stay heavy if we don't change it to light. So for example, this in some previous query, for example, we could have in some previous queries we could have this vertex and then this vertex. So we made this vertex, this edge heavy, and it stays to be heavy. But in some time, for example, if we make query on such vertex, we'll make this vertex light and this edge light, and then this edge will not be heavy. But for example, we made when this edge was heavy, and we don't really need to change it to light. So we just so this edge just stays to be heavy. Is it answering your question? Initial heavy edges are randomly assigned. It doesn't really matter. All of them can be like light. It's not so important. Okay, any other questions about the idea? Okay, let's continue. So, as I said before, let's use display tree. So let's see how our node will be different. So here we have pretty much the same as we had earlier, but we are going to have one more link. It's PP. So PP will be some vertex. So for most of the vertices, it will be null, but we should know, for example, for that vertex, we should know which vertex is a parent of this vertex. So that is why we should store PP. So this PP is the parent in the real tree, not in the display tree, but in such graph that we have. So for example, for such vertex or such one, we don't really need to store PP because they're located in display tree, and we can get its parent from the display tree. Yes, so like, for example, we can find its vertex in, like, we can push it to the top, to the root, and then just find the rightest node in the left sun. And in such a way, we can find the parent of this vertex in the real tree. So again, we're going to store PP only for those vertices whose parent is not in the same display tree. We don't change real tree structure. Right now, we don't. Right now. Okay, so yes, let's continue. So how can we find like the first, how can we find the first like vertex in some display tree? So we, in order to go, if we have some query, we should go to the root, and for that we should find the first element that that is like the leftest in our display tree, so that we can make the next edge heavy. So for that we should have such function left. So in such function we are iterating to the root, and in the root we are iterating to the left. So, and if we do that, we will be able to find the first element, so that is the leftist one. Okay, merge. Merge is pretty similar. We just find the leftist element in the right node, and merge it. Cut right. So in cut right, we will split it into two parts. Oh, okay. So in cut right, we will why leftist element is the topest in the real tree. Okay, so question, why leftist element is the topest in real tree? So we are going to store our split tree in such way so that our first element will, the topest element will be the first one, this one will be the second one, this is the third one, fourth one, and fifth one. So we are going to store them in split trees, in implicit split tree, so that, like, if we have, for example, such split tree and such split tree, will be able to store this split tree to the right of these three elements, so that everything will be working. Is it answering your question? Thanks. Okay. Merge. Cut right. So in cut right, we want to make sure that that vertex that is given is the last element in its split tree. So, for example, we want, in this vertex, we want to make this edge heavy, and we should be sure that it doesn't have any elements to the right in the split tree. So we should make this edge light. So, and that is what we are doing here. If it is not the very last element in our split tree, we should split it into two parts. So we are pushing this vertex to the root. If this vertex doesn't have any elements to the right, we are done. This is already the last element in our split tree, so we should not worry about that. Otherwise, it has some heavy edge, and we should erase it. So, and this is what we are doing. We are taking the right element, we are saying that it doesn't have any parents anymore, and we are saying we are finding the leftist element in that new edge, in that new path, and we are saying that it already has a PP, and we are updating both of them. Okay, and now let's look at the function expose. Our function expose will make sure that there is a path between this vertex and the root. And I didn't tell you one more thing. It should not only like have a path between some vertex and the root, it should also, so if we have, for example, after this query, if we ask this vertex, we should erase this edge as well, so that the split tree, like the path between this vertex and this vertex will be, and there is no other edges after this vertex. Okay, let's come back to cut right. Cut right was for, cut right will remove all the edges, all the vertices that is located after this vertex in the split tree. So we should use cut right here because we don't want this vertex T to have any heavy edges. So if we make a path, this vertex T should be the very last element. That is why we are erasing everything we have after T in our split tree. Is it answering your question? Okay, no reply. I assume yes. So after we erase it, we should find the leftist element, and we will update our path until we find the root. So if this vertex, the leftist one, or the topmost one, has some pp, it means that it's not root. And we should make this edge heavy. So we are taking this element and make sure that we're just erasing all the vertices it has to the right from TPP in the space tree. So after we do that, we are sure that TPP is the very last element in its split tree. So we merge it and finding the leftist element. And then when this equation does not hold, we know that T is the parent, is the root. Yes, is the root of our T. Okay, so any questions about that? Okay, let's continue. So some easy functions. We remove some edge. So in order to remove it, okay, so we remove an edge. Okay, so here we are going to support like a few more functions. We want to remove some edge, we want to add some edge, and we want to find the root and find the depth. So we can add and remove edges, but only if each time all the elements will be like there will be no cycle. So there will be a set of trees. So if there is a cycle, it will not work. So what if we want to support adding and removing edges? Let's say that in our tree, B is located closer to the root, and A is the node that is located next to B, but B is between not remove vertex, but remove edge between. So in this operation, we are going to remove some edge between two vertices, between A and B, where B is on the path between A and the root. So if we do that, we want to make a path between B and the root. So you remember I told you before that if we make such operation, then then B should not have any heavy edges as a child. So it means that if A is the son of B, then A will have a PP. So it will have a parent using a light edge. So after that, we just need to say that A doesn't have it, and it will force us to remove it. Okay, now link. In link, we're just saying that, so we want to add some edge between two vertices. So it's enough just to say that the parent okay, so A is the root and B is any vertex. So it's just enough for us to say that APP that the parent of A is B. Find root. We want to find some root of. We want to find the root in some tree. So we just make a path between T and the root, and we are finding the leftist element. Yeah, and actually that's it. We want to find the distance between the vertex, okay, not the, yeah, the distance or depth between any vertex and the root. So we make a path, we make a path between T and the root, and we are finding the number of vertices in our splay tree. Okay, any questions about that? Okay, let's continue. So let's see what we should do if we want to find the least common exactor between two vertices, or LCA. So we make a path between B and the root, and we want to check that if A is located on our path from B to root. So if A is located, then A will be in our splay tree that we just created. So we are checking if the leftist element in the splay tree of A is the same as the leftist element in B. So if they have the same leftist element, it means that they are in the same splay tree, and it means that A is located on the path between B and the root. So A is our LCA. If it is not true, we check the same for B. If B is on the way between A and the root. If it is not, then we should find, so remember that we firstly we made a path between B and A, and then we made we made a path between B and root, and then between A and root. So it means that if we made this path, for sure we would have to break the path between B and root. So we should find where this path was broken. In order to do that, we should find the leftist element in B and find the parent vertex of that vertex. So, and that vertex would be the element that broke our path from B to root into two parts. The first part is that is common for A as well. So that, I mean, first is those nodes that are located on the path between A and the root as well as B and the root. And second one is the path of vertices that is located on a way from B and the root, but not from A to the root. So obviously, in order to find the LCA, we should find that vertex that divided it. So that vertex that divided that path into two parts will be our LCA. Okay, does make sense? Yes. So if we use splay tree, it is possible to prove that all these functions will be working in log n. It's possible to prove only if we use a splay tree. If we use like trip, we can prove, if I'm not mistaken, we can prove only only log squared. But if we use splay tree, there is a proof that proves that everything will work in log n. Okay, so let's support one more feature. So in the previous examples, in each tree, we had a root. And we were not able to change the root. But now, let's see what should we do so that we can change it. Okay, let's say that this vertex is our root. And we want to change it. Let's say, I don't know, like this one. We can make a path between this vertex and the root. So what should we do so that we can change the root? Actually, it's enough just to reverse the splay tree here. So if this element was the first one, it will become the last element. If this element was the last one, it will become the first one. But remove and link already changing the tree structure. Yes, but for example, if you want to find some function on some path between two vertices, you are not able to do that. For example, if you want to find hold on, what can we find? Okay, so it will not work if you should have okay, for most like common functions like min, max. Oh yeah, so right, you cannot find it for minimum. So if you want to find the minimum between two vertices, what the only thing you can do is to find the minimum between each of these vertices and the root and take the minimum, but it will not always work. There may be some element that will force us to find the minimum that is located like closer to the root. So we will check some extra values that will not be useful for us. So let's say, for example, in such tree, we want to find the minimum between this vertex and this vertex. So what we can do, we can find minimum between this vertex and this vertex, and minimum between this vertex and this vertex. But we will also check these vertices, but we don't need to do that. If, let's say, this vertex has 10, 10, 10, 10, and this vertex has 1, so the minimum will be 1, and there is no way we can get 10 from here. So this is what we cannot do right now. So, but if we are able to change the root, then we can make this vertex a root and like expose this function, this vertex, and build a path between this to this vertex. We can expose, yes, you can. You can expose from LCA to PP. But, okay, so let's say that you find that minimum from here to here is 1, and minimum from here to here is 1 as well. And here, so you can check that minimum from here to here is 1 as well. But it doesn't give you any information if there is any ones here or here. So let's say we have one here on such edge, and the minimum between these two vertices is really 1. So you know that if you check the, okay, you got it. Okay, awesome. Okay, okay, so how to change the root? Let's make like some query here. And then in order to change the root, we only need to change, okay, yeah, I will send the presentation. So the only thing we should change is to reverse all the elements in this play tree. And actually that's it. Because all the PP for all the nodes that are connected to this path will stay the same. The only difference will be the order of this splay tree. So the only thing that we should add in order to support the change root is support of reversing some vertices in the split tree. So we are going to have one more flag, and it's called ref. It means that if we need to reverse this node in the split tree, by default, it's false. So, and I think this function is pretty known for those who are good in segment tree or trip. It's like exactly the same in trip. So we are going to have push function that will check if we need to make a reverse for some node. If this node is not null and we need to do that, in order to reverse all the nodes in our tree, in our subtree, we should change our left and right sons. And after we change them, we should like reverse in them as well. So all the elements in left should be reversed and all the elements in R should be reversed as well. So that is why we are doing these operations. And after that, we're just saying that we did the reverse. And next time when okay, so why we should have such function as push? It's for those it's when we want, when we have like we made some reverse operations and we want to get some value in some node or like to do any operations in that. So we should before accessing any vertices, we should use push. So, and that is what we are doing in find. We are pushing, like before trying to access any vertex, we should have push. So we are so here in find, we are pushing this. And after that, we are just doing everything we did before. Yes. So, and we are going to have one more function that is called clean. Clean will, so let's say we have some vertex, not mandatory is the root of our split tree, and we want to do something with that. And if this vertex has some parent that has to be reversed, we should reverse it first. So what we do? Firstly, we go to the root, and then for the root, we push it. And after we are done with the root, we go to the second root, like the child of the root, and push it again. So after we call this clean function, we can be sure that between vertex T and the root, we don't have any reverse flags. And let's have one more function up, which will push our element to the root with play. So we will clean everything first and then use display function. So right now our display function does not support any push operations. So that is why we should make sure that on the path between T and the root in our display tree, there is no any reverse flags. Does it make sense for everyone? Okay, so our left element will, why all of this works for log n is magic. So I don't really have time. It's like, I was asked to make everything in 1 hour and it's already 1.5 hours. So sorry, I don't have time for that. I will send you the links and you will be able to read that if you're interested in that. So I really hope we can finish at least in 2 hours, but I don't promise. So our left function will be changed. So we can just use find here, find the very first element. cut right, the only thing will be changed is we change splay to up because we also need to clean it first, or alternately, we can just call clean function here and splay function here, but it's actually the same what up is doing. And let's look in our make root function. So first we are going to build a path between t and the root. And then up. So we are going to make sure that there is nothing between t. There is no reverse flags between t and the root. Oh, sorry. Okay, here we are. And after we do that, we are saying we are changing the reverse flag, and we are saying that it should be reversed. Okay, how looks like our link and remove functions right now? So if we want to add, so now we can add edges not only between the root and any other edge in and any other vertex in some other tree, but we can add edges between any and any vertex. In order to do that, we can make the root, and we can make A the root in our tree, and then just add an edge between A and B. And how remove works? It works like in a very similar way. We make a root, and then we make a path between A and root. But since A is already a root, it will force us for our root not to have any heavy edges anymore, so that we are able to say that BP is null. Okay, so do you have any questions about that? Okay, so any questions? Okay, then the very last thing that I want to tell you is what if we have some operations not on the paths between two vertices? So for example, if we know how can we change roots, we can find some functions between two vertices. For example, find the minimum, find maximum, change the remove edge, add edge, but we also are able to find such functions, for example, find the number of vertices in some tree, or find the sum of all elements in some tree, and some other functions that we do not only for the path between two vertices, but for all the tree that we have. So let's, for example, here, let's support the function find the number of nodes in some tree. So here we're going to have add function. This add function will store the add will store the number of nodes that are not located in our splay tree. So add, so for example, okay, no, let's explain it in a little bit different way. So add for some vertex will be the number of elements in the subtrees with which it has a light edge. So for example, for this vertex, we should have two, because we have this vertex and this vertex. We should not store any information about, like, we should not store the number of elements in this splay tree because we can get it. But we should store the number of nodes here. For example, for this vertex, the added will be 1. And for this vertex, it will be 1, 2, 3, 4, 5, 6, 7. Okay? Okay, so what's changed here? We have add here, and we are saying that add is 0 by default. So how is update work? So our size will be our update function will be changed. Now we also have, so when we are counting the size, we are also counting the T8 in order to, like, when we want to find the number of elements in some splay tree, we will also count all the splay trees that depend on them. So I mean all the splay trees that are lower than that one. So for example, this splay tree is lower than this one, and all other splay trees are lower than this one. So that is why we should update our update function. So merge. So what's the difference in our merge? So if we merge two elements, so it means that there was a light edge between two paths, between two vertices. What is added? Okay, so what is add? Add for some vertex is the number of vertices that is connected by light edge. So for this vertex, the add will be 2 because we have only one light edge, and it's this one. So, and let's count the number of elements in this subtree. It's 1 and 2. So add for this vertex will be 2. And add for this vertex will be 1, 2, 3, 4, 5, 6, 7. So, and that is what we store here. So you can think about this in such a way. So for this vertex, we have PP, and this PP will be the root. So when we make a connection between vertex and the parent, for the son, we should have the PP, because we should know who is the parent of this vertex. And for the parent, we should know how many elements his children have. We should not really know like the links to his children. We should know only how many elements are there. Does it make sense for you? Okay, awesome. So merge. So when we have a merge function, we should, so we call merge only for those paths which is connected by a light edge. So you remember that we have this PP. If we make heavy edge from the light edge, we should remove PP. So, and also we should remove the add for this new parent. And what else is changed here? Oh yeah, and this we should be able. Okay, yeah. So we should find the leftist element in the right part and the rightest element in the left part, so that we can change the add value for this node. Okay, any questions about that? Okay. Cut right. So what difference we have in cut right? If we make some vertex slide from heavy, we should make, yeah, here we are making PP equal to this vertex. And also for this vertex, we should add the size of that subtree that we are cutting. Yeah, actually that's it for cut right. Okay, so how link is different? If we add an edge between two vertices, we will make we will add a light edge. So if we have a light edge, we should also change the add value. So what's the difference? We make a root of A, and we find the path between B and the root. Display A. So A is the root in our display tree. So if A is the root in our display tree, if we call the size function, we will be able to find the number of nodes in its subtree, in the whole tree, not only in the display tree, but in the tree as a whole. So this function will let us know that, and we will be able to add this value to be add. So then we update it, display it, and say that the pp of A is B. Okay, next, remove is pretty similar to add. We just removing that, not adding. Okay, we are almost done. So, and the very last slide that I want to show you is get size of tree. So if we want to get the size of some tree, we make the path between T and the root. We push it to the up, and we are finding the size of this value. So because T will be the root, and the value in the root will mean the size of the root will mean the size of the whole tree. Okay, that's it that I have for you. What questions do you have? When the contest starts and will it be thematical? It will be very thematical, and there will be a few problems that you don't need to know Linka 3 for that, but there are just a few. Can you show size function? Size function, size. Huh, where is that? So size function is actually, it was last slide. This one. So like size is just t size. If t is null, you return 0. If t is not null, you just return t size. And size is some variable in the node. Okay, any other questions? Please share your presentation before the contest. Okay, I will do that. No worries. I will send it here in the Zoom and in the Telegram chat as well. This will not help, I think. Okay, since you don't have any questions anymore, will you send all the code of Linka 3? I will send only this presentation, not the code. Let me do it right now. And I will send it in Telegram group as well. Okay. Do you have any questions? If not, okay, then if you don't have any questions, then okay, I will send additional resources in the e-judge as a Clara. So we will make, how many minutes do you need to take a break? Like 5, 10? Just type to the chat. What do you want, 5 minutes or 10 minutes? 5 minutes, 15, 15, 10, 10, 15, 10. Let's start at 11. Okay, then we are going to start in 11. Okay, I changed the start time. So if you update, if you log into eJudge, you will see that it will start exactly at 11. Okay, if you don't have any questions, I think we are done. Thank you for listening to me. I know it was for long and it was pretty boring, I think. I know that. Sorry about that. So if you have any questions, please feel free either to message me in Telegram or in Telegram chat. Okay, thank you. See you.